Very good evening, all. Welcome to day 4 of short course program on metrology and mechanical measurements. Today's topic is angular and geometric measurements. This session primarily focuses on the basic principles, instruments, techniques, and practical applications required for achieving precision, accuracy, and quality in engineering measurements. In this session, we will cover 5 major important areas: fundamentals of angular measurement, angular measuring instruments, geometric tolerances, and geometric dimensioning and tolerances, measurement of straightness, flatness, roundness, and cylindricity, and finally, practical applications and best practices. So now let us begin with the fundamentals of angular measurement. An angle represents the divergence between two lines or planes meeting at a point. Angular metrology is concerned with the generation, transfer, measurement, and verification of angular values with higher accuracy. Angles are commonly expressed in degrees, minutes, seconds, and radians. One complete revolution is 360 degrees. 1 degree is equal to 60 minutes, and 1 minute is equal to 60 seconds. 1 radian is approximately 57.2958 degrees. For precision angular measurement, reference standards such as angle gauge, polygons, and precision indexing tables are used. Measurements may be performed using direct reading methods or indirect comparison and trigonometric methods. Accuracy can be influenced by several factors including temperature, instrument alignment, parallax, and operator technique. Therefore, proper measurement conditions are essential for obtaining reliable results. Now let us examine the angular measuring instruments and its various types. The bevel protector is used for directly measuring angles between two faces with its vernier scale providing fine angular readings. The sine bar is a precision instrument used with gauge blocks for setting and measuring angles accurately. Angle gauge blocks can be combined in different arrangements to produce precise reference angles. The autocollimator is an optical instrument used for detecting very small angular deviations and for alignment applications. Clinometer or sprit level measures the inclination of surface relative to the horizontal or vertical. The angle decker uses an optical projection principles for angle comparison in production environments. Let us look more closely at the sine bar principle. A sine bar is used together with slip gauges to establish a precise angle through a trigonometric relationship. The fundamental equation is sine theta equal to h divided by L, where theta represents the angle, h represents the height established using gauge blocks, and L represents the distance between the centers of the sine bar rollers. The sine bar is generally more suitable for measuring or setting angles below 45 degrees. It is normally used on a surface plate along with slip gauges and a dial indicator. For accurate measurement, the rollers must have equal and properly calibrated diameters. Next, we come to the autocollimator. An autocollimator projects a collimated beam of light onto a reflector mirror. When the mirror is tilted, the reflected image shifts. This shift can be measured to determine extremely smaller angle deviations. Autocollimators are useful for straightness and flatness testing, squareness checks, small angle measurements, alignment operations, and calibration of angle gauges and indexing tables. We will now move to the geometric dimensioning and tolerances. Geometric dimensioning and tolerances defines the allowable variation of engineering futures in terms of form, orientation, location, and runout. It provides a systematic approach for controlling geometric requirements beyond simple dimensional tolerances. Form controls include straightness, flatness, circularity, and cylindricity. Orientation controls include parallelism, perpendicularity, and angularity. Location controls include position, con- concentricity, and symmetry. Runout controls include circular runout and total runout. Understanding this geometric requirement is essential for manufacturing components that meet functional and assembly requirements. Let us now consider straightness and flatness measurement. Straightness describes a condition in which every point of your line lies within a specified tolerance zone along its intended direction. Straightness can be evaluated using instruments and techniques such as dial indicators with V blocks or surface plates, spread levels, autocollimators, and laser interferometer. Typical applications include mission slideways, shaft, guide rails, and precision edges. Flatness refers to the condition in which all points of a surface lie within two parallel planes, forming the specified tolerance zone. Flatness measurement can involve a surface plate and dial gauge, autocollimator, grid methods, or optical flats for very fine surfaces. These measurements are particularly important for mission tables, sealing surfaces, and mounting faces. Next, let us discuss roundness and cylindricity. Roundness, also known as circularity, requires all points on a circular cross section to remain within the specified tolerance from a common center. Roundness can be measured using roundness testing machine, a V block with a dial gauge, or a micrometer measurements at appropriate sections. Cylindricity is more comprehensive geometric requirement. It combines the concepts of roundness and straightness, ensuring that the complete cylindrical surface lies within the specified coaxial cylindrical tolerance zone. Measurement can be carried out using roundness machine with axial traverse, a coordinated measuring machine, or micrometer measurements at multiple sections. Let us now look at the practical application and best practices. Angular and geometric measurement are important in machine tool alignment and acceptance testing. Precision fixture and jig verification, bearing seat and shaft roundness inspection, inspection of ground and lapped surfaces, calibration of angle gauges and sign bars, and quality control of automotive and aerospace components. For reliable measurement, always control the measurement environment and maintain a stable temperature. Clean reference surfaces before measurement and handle precision instruments carefully. Minimize operator errors by avoiding parallax and applying consistent measuring force. Ensure that the measuring instruments are calibrated regularly and traceable to appropriate national standards. Finally, record measurements systematically and take multiple readings at different positions whenever required. Repeatability and consistency are essential characteristics of good measurement practice. To conclude, angular and geometric measurement form an essential foundation of precision engineering and quality control. This session is especially useful for engineers, faculty members from various colleges, researchers, diploma students, and engineering students. By the end of this today's session, participants should be able to strengthen their core measurement skills, improve the accuracy of angular and geometric inspection, and understand how precision measurement contributes to product quality and reliability. Thank you for being a part of day 4 of this short course on angular measurement and geometric measurements. Thank you, and I wish you a successful learning experience.